Christina actually asked, is this a mistake here? Like, think lazy. Like, shouldn't it be think lazily? No, we're being even lazier. This work that I'm going to present is collaboration with Itzel Olivos Castillo and Paul Schrader, and it was funded by the Air Force Office of Scientific Research. And thank you for that amazing opportunity to collaborate with these awesome people. So what are brains for? Brains are for doing stuff. Agents, yay, agents. You've probably heard this amazing story of the sea squirt, this little sea organism that its larval childhood phase is moving around, and then it finds a rock, and then its first job in adulthood is to sit on that rock forever. And it never moves again, and its first order of business is to eat its own brain. Yeah, I think Daniel Wilbert was the one who brought this one to my attention. It's super cool. Cute too. So the problem is that, like, why do you want to eat your brain? Because thinking is hard, and so why should you pay resources for something you're not going to use? And there's plenty of research, for example, this work from Natalie Rochefort, showing that when you're metabolically challenged, you change your thinking. You change the way that the activity of the neurons works. And we know that our brains have undergone a lot of pressure to save energy. So if you compare the wattage of our brain versus ChatGPT, it's orders of magnitude. Now, you might also say, as Alex Kulikov has pointed out, that ChatGPT produces a lot more text, a lot more more rapidly than we do. So we have to be careful about balancing all those numbers. But at any rate, like, maybe it's better to be a bit dumber and just act a little differently to account for that, and we can do well enough. So Hannah introduced this nice action perception loop. Here we're going to be talking about action perception loops. And so we have our neurons, which we're going to imagine represent some beliefs about the world. And those beliefs are used to justify or guide actions, which then affect the world. The world has its own dynamics. And then we only get partial observations about that world. And those partial observations come back to our neurons to update our implicit beliefs about all of that. And there could be various constraints along the way, like constraints in physics, constraints on your body, constraints on your algorithm. And here we're thinking about implementation constraints, which is constraints on the meat in your skull. You have to burn calories in order to think. Who here loves POMDPs? Please, everybody raise your hand. All right, yes. So POMDPs is a beautiful framework for capturing this structure that I just talked about. Very natural description of tasks. POMDP stands for partially observable Markov decision process. It's a process because it unfolds in time. It's decisions because you keep taking actions. It's Markovian because that whole thing is memoryless in the sense that the change only depends on the current state. And it's partially observable because you don't get to know the real world. You only get to know observations of it, which tell you imperfect information. So the world is marching along from left to right over time. The state of the world is some S, t, and the updates are only p of s t plus 1 given st. So you don't have to know the more distant history to know how physics evolves. Then we get these observations of the brain according to some probability of the observations given the state. And we use those to construct a belief. Now, you can do this optimally. And if we did so, we might say that the belief, which is a posterior about the world, is a probability of the current world state now, given all the observations up to and including the current time. So this so far is just a hidden Markov model. Then we add in the actions, and we add them both as an effect on the world and an effect on the belief, because we know that we're changing the world. And we draw those actions from a policy, which has, in this case, a probability distribution over actions given our belief. Right? And we choose that policy and optimize the whole system in such a way as to get the most that we can out of the world. I mean, ultimately, brain's job is to make more brains, but we might have a more narrow view than that. So most of that is describing the process that we use for reinforcement learning and or representation learning. So you have some reward which you're trying to optimize, which is a function of the state of the world and what you did, and the actions, the costs that it took you to take those actions. If it's partially observable, then the world is your reward that you're estimating is the expected reward under your belief state. But now we're going to introduce some extra costs, which are your brain costs, the cost of your representation and the cost of your computation. And today I'm just going to focus on the representation cost here, H of R. This is H, you could imagine, might be the entropy. So the dictionary of possible, the range of possible answers that you have. There's other ways that you could quantify the representation cost. I'm not going to talk today about the computation cost, but there's some fun stories there too. So today's focus is, again, going to be on that representation cost, which leads to something that we call frugal inference for control. Frugal meaning that you're not doing the best possible inference. You're deliberately leaving some things out, but you're doing it in such a way as it optimizes your total objective. So first, the way we're going to approach this problem is we're going to define the unconstrained control problem. Then we'll define some neural costs, and then we'll optimize for both of them together and interpret. So many of you are familiar with this whole body of work on efficient stuff, like efficient coding. Lots of very influential work thinking about how we can take the information and represent it efficiently, that is, using little metabolic costs. Sometimes people talk about efficient decisions. I like this top one, which is by Ed Vull, one and done, where you take a single sample and you say that actually is the best thing that you could do under some constraints, or bounded rationality or rate distortion theory, a wide range of topics there. Less is done about efficient control, where you're actually paying costs for thinking leading to control. This bottom one here, the CMU, I don't know how to say that actually, is studying how should you best perceive the world in the sense of like what sensing apparatus should you use to support control. And here we're instead going to use how should you represent the computations or the beliefs. So here we have this loop again that we can imagine a rolled up POMDP. And so now what we're going to do is take this state, action, belief, observation, or the arrows backwards there. Oh, no, that's right. The state gives rise to the observations, to the belief, to the action. And those two, you have costs from the state and the action. But now we're going to add this cost. You're going to have a cost on your belief. Okay. So if you're going to have a lot of information, you're going to pay for it. So now to formulate this problem mathematically, we're going to imagine that we're asking for control of a partially observable world state, and we'll make that unstable. So it's really important that you actually control it. If you just let the world alone, then your reward state, your state cost is going to blow up. Neurons have to integrate information history, the observations over time, to correct and do so in a way that correctly, in some notion of correct, weighs the new evidence. But representations are costly. And we'd like to compare, if you're resource constrained, how does that compare to the unconstrained one? And we're going to do this in a classic linear problem where we can solve the math. And so let us not forget that esteemed history of people studying very simple problems in order to get insights. And NeurIPS reviewers, if you're listening, it's okay to study linear quadratic control problems. We've gotten some insight from them. Okay, so we're going to base this on the Kalman filter. Kalman famously derived the Kalman filter, which is the best way of doing inference. And then he also studied control. And then he also put those two together with linear quadratic Gaussian control. So here's the LQG problem. And we're going to modify this problem to be frugal about it for control. So in the LQG problem, we have a world state S, which has some linear dynamics multiplied by some matrix A. Here I'm just going to talk for a while about scalars. So a constant A times the old S. And here A is going to be bigger than 1 because it's going to be unstable. So you can see this blue curve, which is the world state over time, is blowing up. So it's getting worse and worse, and our cost is getting worse and worse. But the world is affected by some input, which is the input gain B, and some control here U. And then it's also got some stochasticity to it, the non-predictable part. And so that's some process variability eta. Then we get some observations. Our observations are a linear projection of the world plus some observation noise. And then we construct our estimate, which according to the Kalman filter would be some weighted combination of our old estimate S hat plus our knowledge of our action that we just took, because we took it, we know what action we took, at least in this framing, plus some weight on the new observations that we get. And ultimately, our control is going to be based on, it's linearly proportional to our estimate. So if you're far away from the origin, you're going to take a big step back toward the origin to regulate it. If you're close to the origin, you'll take a little step back to the origin. And the control gain is L. So that tells you the proportionality. So let me go back here and I just want to show you the dots for the observations. And then the control is coming now. To solve this problem in our case, we're going to put all of those variables into one big vector. So you have the state, the estimate, and the control as one big vector Z. And then we just have a single linear dynamical system with stochasticity for Z. So there's some dynamics matrix M that covers all of those parts, and there's some noise which covers all of those noises. And ultimately, our objective at equilibrium, so we're going to do this for a long time and just wait till the system settles down. And our objective depends only on this, ultimately on this covariance matrix between all of these things. So it depends on the variance of your states, how much of you actually wiggled around compared to you're trying to keep things stable. How much control are you exerting? So you have this U squared here. And then you have the state estimate, which is going to be related to how much you're paying to think. Okay, so if you have a lot of variability, then and you have a given precision on that, then you have a lot of information. And we're going to come back to that in a minute, but you can see that all these terms in this covariance are going to influence our objective. So now we put in the costs. So the cost here is the variance of the signal, the variance of the actions, and this is classic LQG. And so if we're trying to optimize just here, when we turn on the controls at this time, now the state is no longer blowing up. The whole system in closed loop is no longer unstable. We've stabilized it by the controls. And we end up with something which is still wiggling around because the world state is itself uncertain and we can't predict the future. And we get noisy observations. So both of those things together make it hard to control. But we do a decent job of controlling it within some range, and we find the right balance, LQG optimal. Now, we add this new term, which is our cost on our neural representations, which here we're embodying as the cost on the estimator, okay? And when we turn on that objective, we change our whole system, we change the way that we integrate new observations, and we change the way that we control, given those representations. We actually now have a different dynamics under control, which in this case, the state under bounded control is still kept under wraps. You're not blowing up, it's stable, but it's, in this case, is more wiggly. So what cost do we have? In this case, we put information cost. So this is the information between our estimate and the world. So if you're going to have a very informative belief about the world, it's going to be reliable, you're going to pay for it. So if we formulate this as an overall objective, we can sort of summarize this unbounded control and compare it to bounded control and see that both of them we're going to be treating as linear problems. They're both estimates that are weighted sums of our past estimate and our new observation. But when we're doing the bounded rational control or this frugal inference, we're not going to use the Kalman gains. We're not going to use those optimal characteristics. Instead, we pick some alpha and some beta that optimizes our total cost, including the representation. And we're still going to have a linear control. So now what happens is that in the unbounded case, we're going to pay three costs. We'll pay a state cost, which we're trying to minimize, basically keep the state close to the origin. We have an action cost of moving, and then we have this information cost. And when we modify this, we actually are going to move more in order to think less. So our information cost is going down, the total cost is going down, but at the additional expense of taking more actions. So we're thinking lazy, but we're taking some more energetic movements. And overall, there are cases where this is beneficial. The optimization landscape actually now no longer has a single optimum, which would be this diamond here, but it bifurcates into a family of equally good optima. So here there are two, and we can name them. One of them is is naive and reactive. So it's credulous. It believes all of the observations and then reacts immediately to them as if it trusts them perfectly. And then there's the skeptic, which is like, I don't think so, and it integrates longer, weighs its model more, and then synthesizes that information and relies on the world to kind of correct itself. So it's skeptical and serene. I personally am more in that camp, maybe. It turns out that there are phase transitions in when these strategies occur. And so sometimes it's best to actually be optimal, and other times it's best in the global sense, like the total cost, to be to take one of these suboptimal or frugal inference strategies. So we try this on a couple of different systems. We have our Roomba that we code up, and you can see the different trajectories here. The naive reactive and the serene skeptical Roomba both have the same final performance, but one of them is wigglier than the other. And in more dimensions, you actually have a whole hypersphere of families that are exactly equal in all of the task costs, which is kind of fun. Here's a one-dimensional parameterized family, and you can see that the memory factor on the past and the control gain, those depend on, for these 2 dimensions, which particular family member you have. And they generalize differently over new tasks. So if you're worried about the worst case scenario, you might pick one particular kind of suboptimal or bounded optimal strategy. And if you're worried about average case, then you pick a different one. So we have these agents. They're doing their things in LQG. Right now, they're optimized for one environment, but the whole point is that you want to be able to adjust your strategy according to the statistics of the world. So if you just had one world, you could say, well, I don't even need to represent this as an interesting information filter. I just have a weighted sum, like an exponential integral of my past. But if the world reliability is changing for some reason, now you want to have a dynamic representation of when should I weigh the past more, when should I weigh it less. So that we're working on that. So to summarize, we talk about this bounded rational control when information is costly, whereas conventional states only penalize the states and actions. Here we penalize the brain, embodying the meat of the brain. And we turn out to see phase transitions, totally different regimes, in when integration, being smart, is useful for control. So we take this task framework, which we had this extra orange arrow, and now we add in a little bit of embellishments to show, hey, now as the world dynamics change, the strategy you take should change. And that includes for your memory, for your sensitivity, and for your control gain. So with that, I want to thank Itzel and Paul again, and my funders, and thanks for your attention. Happy to take questions.
Hello, very nice talk. I had a question. So when you add this additional term to your cost function,
Yep.
You are imposing the optimal policy to be linear, or is this actually optimal?
No, we're imposing it to be linear.
Okay. Do you get a sense whether this is optimal?
I mean, for linear, I'm not sure. I don't.
Yeah, I just asked because we know in the other case, right? When you don't have that cost, being linear is actually optimal.
Definitely
but
linear.
In this case, I'm not sure.
Yeah.
Yeah.
Well, one thing that definitely changes is you no longer have the separation principle.
I bet. Yeah.
Right. So you're now your policy, your actions that you take should no longer be independent of how you're choosing to weigh them.
Yeah.
So that breaks from the classic LQG setting.
Yeah.
And so maybe in that sense, there's going to be, well, there are definitely correlations between the control gain and the Kalman gain, the effective Kalman gain. But I don't know whether that leads to breaking the linearity. On the other hand, ultimately, who here really cares about linear problems? Just instrumentally, right? So the real problem is going to be nonlinear, and so that question becomes less material when you deal with, actually balancing on one foot, or controlling a drone, or finding a mate, etc. So, but I think it's a really interesting question, and I would love to know the answer, but I don't.
Okay. Okay, and just a follow-up question. So the LQG is a particular case of a more general framework that is called LEQG, which has like risk sensitivity embedded into the cost function. So I was wondering if you could do something similar for the more general case, and then this could be like a particular case, or?
Yeah, I think the risk sensitivity is an interesting case there when you exponentiate the cost. And there are some nice relationships also with Todorov's work on KL control.
Indeed,
that would be nice. We're very eager to generalize this. The first step to generalizing it is going to be doing more of like a reinforcement learning, machine learning context where you just give it enough resources to learn good inferences and policies when you change the objectives to have these internal costs. And then after we get some sense of that, we'll go back and we'll see if we can do some more theorizing.
Cool. Very nice. Thank you.
Thanks. Really cool talk. Slightly more on the RL side. Have you also thought, like the system's complex enough, but have you also thought of if you can only control or have actions that influence specific states? So you have kind of partial observability, a partial action controllability, and how that kind of changes this setup, or if you have intuitions on that.
Yeah, that's a great question. And actually it plugs into some other projects that we're working on with a few people in the audience here. Controllability, I think, is a really important ingredient, and you should not bother gathering information and synthesizing information about things you can't do anything about, which is why I don't read the news. It's also not true, but I wish it were true. So I think that that's an important consideration if you really care about saving thought power. And I think many people actually do, like ostriches, maybe noteworthy, do take that kind of strategy. So yeah, I think that's important.
Entropy kind of becomes an interesting point there, right? Like there's these classical RL papers where you have like a noisy television and you have high entropy and you can keep changing it, but it doesn't actually change your state or kind of what you can do in the environment.
Yeah, that's right.
So you change the cost function that way.
If you just had a curiosity kind of motivation, then you would just be looking for maximum information. And if it's of no use to you, then don't bother. And I think Sherlock Holmes actually took that strategy. He says, like, if the sun goes around the earth or the earth goes around the sun, doesn't affect what I do. It's some entropy out there. I'm going to ignore it.